Professor Mikhailo Dokuchaev from University of São Paulo, and his talk is a 7-term exact sequence related to an extension of commutative rings and a partial representation.
Thank you very much. I thank the organizers for giving me an opportunity to talk at this remarkable event. I'm going to speak about a joint work with Itaíma Rocha, and the story there is some. Can you see the full slide?
Yes, it's okay.
For me appears is it okay this way, or is it better?
No, go back, please.
Go back.
It was full screen. Okay.
Okay, so I just don't see my upper line because of some symbols here, but never mind. So the story starts with a paper of Auslander and Goldman, in which they defined the concept of Galois extension for commutative rings, separable algebras over commutative rings, Azumaya algebras over commutative rings, and the Brouwer group over commutative ring. Further developments on Galois theory of commutative rings was given in a paper by Chase, Harrison, and Rosenberg of 65, in which they gave equivalent definitions of Galois extension, a Galois correspondence, and also established the following 7-term exact sequence, which involve various cohomology groups, the first one, the second one, the third one, with values in the bigger ring, the Picard group, fixed point of the Picard group of S, and also the relative Brouwer group of the ring extension, also the first homology group with values in the Picard group of S. They applied another sequence, 7-term sequence, published in the same volume, Memoir of IMS, from the paper of Chase and Rosenberg, related to arbitrary extensions of commutative rings, and that involve Brouwer groups and Amisul cohomology, and they proved it using spectral sequences, and that was not a constructive proof. A constructive proof was given by Kanzaki using the concept of generalized cross products. Details can be found, some details can be found in the book by De Meyer and Ingram. The above sequence generalizes two fundamental facts of Galois homology. The first one is the Hilbert-90s theorem, proved in general form for commutative rings in the same paper by Auslander and Goldman. So we have an extension of commutative rings, a Galois extension of commutative rings with finite Galois group G, and assume that the Picard group of R is 1, and then the first cohomology group of G with values in US is 1. If we come back to that sequence, it is an immediate consequence of that, right? Okay, if the speaker okay. So another why this is theorem 90? For fields, it was proved by Emil Noether in 1933, and it's called Hilbert 90 because it is theorem numbered by number 90 in Hilbert text of number theory of 1897, in which he gives a theorem proved by Kummer in 1855. So that's for the case of finite cyclic Galois extension of fields. So we have a cyclic Galois group generated by sigma, and for any element A of the bigger field L, whose norm is 1, there exists an element B such that A is sigma B over B. So this can be reformulated by saying that the cohomology group, first cohomology group, is trivial. Another theorem generalized by the sequence for commutative rings established in the same paper by Auslander and Goldman. So if you have a Galois extension of commutative rings with finite Galois group G, and if you assume that Picard group of S now of the bigger ring is 1, then you have the isomorphism of the second cohomology group of G with values in S, U of S. U of S means invertible elements of S. And this is isomorphic to the relative Brouwer group of S over R. So if we come back to that sequence, we have this isomorphism. And this group and this third group are trivial. Okay. Well, and the isomorphism is given taking a 2 cocycle and using it as a factor set. One defines a cross product. So we have the Galois action of G on S, and using that factor set with cocycle, we can define a cross product. And its equivalence class is the element of the Brouwer group, which gives the isomorphism. Now, a non-commutative version of this was given by Miyashita, and he uses the idea of Kanzaki of generalized cross products. It is a different looking sequence, but the Chase-Harrison-Rosenberg sequence can be derived from that. And it takes an extension of non-necessarily commutative rings and a group homomorphism from G to the group of invertible sub-bimodules of S, R sub-modules. So S can be seen as an R bimodule. We take R sub-bimodules, which are invertible in this sense. So he takes this homomorphism, and attached to this homomorphism, he gives a sequence. This Miyashita sequence was extended by El Kautit and Gomez Torresillas in papers published in Journal of Algebra. Formally speaking, it was in the paper published in 2012, but they use much information results from the paper of 2010. So they extend it for the case of non-commutative rings with local units. So in the bulk considerations, about results that the rings will with unity, with unit element. They generalize to local rings with local units. And also attach the sequence to the same time of same types of homomorphism. There are other versions of sequence in other contexts. One of them is for topological context and sister algebras. It was given by a paper published in 2007 by Crocker, Lilburn, and Williams. Well, we have the concept of Galois extension, Galois theory based on partial actions of commutative rings. So we extended this sequence, the Chase-Harrison-Rosenberg sequence, for partial Galois extensions in a sequence of 2 papers. The first one is Antonio Paques and Hector Pinedo. In this paper, we constructed the homomorphisms, and in a paper with the same authors plus Itael Maroscia, published in 2021, we proved the exactness of the sequence. Now, our idea is to do a non-commutative version, and instead of homomorphism, take what we call a partial homomorphism. So I mentioned that in non-commutative context, the homomorphism, the sequence was related to a certain type of homomorphism, and we will take as what we call a partial representation. But I need to give some definitions. I start by defining what is a partial action. It was defined yesterday in a section in a talk of Gabriel Vidal from Brazil, but I recall it. So if you have a group and access set, the partial action consists of subsets the sub G and bijections between subsets. So the domain is indexed by G by D, indexed by G inverse, right? And range by G. So what is that? If you can apply H to X, and then you can apply theta G to the result, then we require that you can apply GH to X, and the result will be the same. So GX by thetas, which are partial bijections, bijections subset, and I say that G applies to X or H applies to X if X is in the domain of theta sub G. And we also require that the identity element X trivially on all elements. Examples. Any flow you can imagine. If you think of the wind blowing in Kiev, you can take a particle and wait some time. So the action is going to be of the additive group of real numbers by time passing, right? So take an article in Kiev, take a particle in the air of Kiev, wait, say 5 seconds. And suppose that if after that you can wait more, say 7 seconds, the particle is inside of Kiev. So you wait 5 seconds, the particle is in Kiev. After 7 seconds, again, the particle is still in Kiev. So it's the same thing that to wait 12 seconds in begin with, and your article will be in Kiev, and the result is the same. So this is the idea of a flow, and mathematically you can take a smooth vector field and the flow of it, and it is a genuine partial action of the additive group of real numbers on a manifold. Another example of the projective 2x2 matrices over the complex number act on the complex plane by Möbius transformations, or another term, fractional linear transformations. So you see that the denominator could be 0, so you need eventually exclude a point from the complex plane. So this is a partial action. It can be seen that is a partial action of this projective group. Well, partial actions are related to the concept of partial representations. In which way? Let X be a set, so we take IX, the set of all partial bijections of a set, and then if you have a partial action, then of course H theta G is a partial bijection. So when such maps from G to IX, which is the set of all partial bijections, determine partial action. So it was shown by Axel in the paper of 98 that this happens if and only if the following two properties hold. So you see the identity map is the identity permutation of the set. And of course, here we take composition of partial bijections. So it is defined, it is a known operation in the theory of semigroups. If you have two bijections between subsets, the range of one may not be equal to the domain of another one. By taking intersection, you can define the composition on the largest possible domain. So in this sense, we take composition of partial bijections here. So you see that theta in general does not respect the product, but it respects the product if the both sides of the equations are multiplied by theta G inverse. If this holds, then as a consequence, one can show that also property 3 holds. So you can multiply now both sides of the equality by theta G inverse, and then you can join or open the brackets with theta GH. Of course, any representation is a partial representation. So this gives us the idea of the following notion. A map from a group into a monoid called a partial representation if satisfies all these 3 properties. So I said 3 is a consequence of first 2. This is only in the case of this monoid. This is a monoid. It's a famous monoid. It's the symmetric inverse monoid of a set. But for general monoids, 3 is not a consequence on 1 and 2, so we require all 3 properties. Now, just it is an exercise, so this information I will use below. So if you have any partial representation of G into a monoid S, then we denote by epsilon G theta G times theta G inverse. It is shown, it is an exercise to see that they commute these epsilons, they are commuting idempotence in the monoid, and moreover, these equalities hold, and I will recall them when I use them. So the background for, I mentioned, so we have a theory of Galois theory of partial action. This was introduced in the paper with Miguel Ferrer and Antonio Paques in 2007. And we also have cohomology based on partial actions. This was introduced in a joint paper with Mykola Kripchenko in 2015. And now, in this cohomology theory, what are the G modules? These are partial G modules in the following sense. They are commutative monoids with a partial action of G on A called theta. And these partial actions are unital in the sense that each domain is an ideal generated by a central ident. Now, let me recall that a module over a non-necessarily commutative ring with identity is called invertible. If there is a module, a bimodule, sorry, a bimodule is called invertible. If there is another bimodule, which there is an isomorphism like here. And the Picard group of non-commutative ring is defined as an isomorphism classes of invertible R bimodules with products induced by the tensor product. There are equivalent form of this definition. So bimodule is invertible if and only if it is a finitely generated projective generator, and there is this isomorphism with endomorphism ring, and also equivalent to a symmetric property in which we, instead of write P as a right module over R, we take P as a left module. So the inverses are given by the dual modules. In this case, the dual and right dual are isomorphic as bimodules. Now we introduce the concept of a partially invertible bimodule. So we require that they are finitely generated projective on both sides. And those maps which were isomorphism in the previous slide, now we require that are only surjective, only epimorphism. And so the set of all isomorphism classes of partially invertible R bimodules via endo with the structure of a semigroup. It is a monoid, and the operation is induced by the tensor product. And the unit group of this monoid, this Picard monoid, is exactly the Picard group of the non-commutative ring. If R is a K algebra of a commutative ring, then we denote that we consider the following subgroup Pic S K, which is the subgroup of Pic S formed by those bimodules on which the action of K is central. So the left action of K is the same as the right action of K. So taking extension of non-commutative rings, we will define a generalization of that group which Miyashita considered. We take sub-bimodules of S, and we define the multiplication like Miyashita, but Miyashita takes invertible bimodules, we take all. So it is a monoid whose unity element is R. And we are going to deal with a partial, so Miyashita took a homomorphism from G to invertible elements in this monoid, but we are going to take a partial representation, right? And we require this should be unital, that epsilon x from one of the previous slides, which are commuting idempotence and so on, should be generated by a central idempotent of R. And so by this we mean a unital partial representation. If you take such a partial representation, theta x, of course, is going to be in this monoid, but it also belongs to peak S. So it's a partial invertible. And then we can compose our partial representation with the isomorphism class, and we have a partial representation of G into peak S. Now, a partial representation into peak S is called unital if the similar property holds, right? Now, given a partial representation into peak S, we can define a partial action on the center of R. Denote by Z the center of R and the partial action. So we have to define the ideals. So these ideals in the center generated by this idempotent, central idempotent 1x. And the action is a conjugating like sum where these omegas come from this isomorphism. So we have a partial action. Once we have a partial action over a commutative ring, we can consider a partial cohomology. Because a commutative ring is a commutative monoid with respect to multiplication. So taking a unital partial representation, due to this equality from that exercise, we can form R isomorphisms of R bimodules. Let's call them F theta, this set of isomorphisms. And then we can construct what we are going to call a generalized partial cross product. So we take a direct sum, external direct sum of this theta x, and define a product this way using this isomorphism. It could be associative or not, but when this is associative, we call it a factor set. And then if it is associative, it can be shown as also a unital ring. So it has identity. And we call them partial generalized partial cross products. Now we define what does mean M divides one bimodule divides another one. So M, we say that M divides N bimodules, right? If there is another bimodule M prime, that this direct sum is a direct power of N. And now let's take a partial representation of G into peak S, a unital one, and assume that it admits a factor set. So that cross product is associative. This always happens if our partial representations comes from partial representations into this semigroup S, right? Constructed. These are sub-bimodules of S, right? Sub-R bimodules of S. Then it is always going to be a factor set, and the cross product, generalized cross product, is always going to be associative. Now we define the abelian group of generalized partial cross products. So these are isomorphous classes of cross products defined above for those gammas such that gamma x divides theta x. So theta is a given partial representation, right? And then we take other ones such that gamma x divides theta x, and they are unital, right? And then we prove that this is an abelian group where multiplication is given by this way. Okay, so this kind of multiplication, and the proof is sort of long, okay, of this proposition. For a unital partial representation, we also define a subgroup of the Picard group. So it's a group, this is a group, and this is a subgroup defined this way. So it's kind of invariant, sort of invariance. And we show that this is a subgroup. Given an element from this subgroup, we denote by omega x, P above is this kind of tensor conjugation of theta x by P. And then what happens that if we take any P from this subgroup and map it to this omega, then we have a unital partial representation. Moreover, each omega x will divide theta x in the both sense, and moreover, each omega admits a factor set, so it really gives a partial generalized cross product. Now there is a theorem. If you take the class of P and send it to the class of the partial generalized cross product corresponding to omega, then it is a group homomorphism. This is also a sort of long proof calculations, but this L and this group C allows us to define the partial non-commutative version of a version of the relative Brouwer group for a non-commutative ring and involving a partial representation in the definition. So this is this factor group. So we cut the group of generalized partial cross product by the image of L. Well, now we define a subsemi group pic S0. So it's those elements from pic S which divide R in the above sense, and we have a partial action on this pic S0. So the ideals are generated by the class of R1X, and the isomorphism are given of this kind of tensor conjugation. We show that it's a commutative semigroup, it's a subsemigroup of pic Z. So Z, the center X centrally on this, so the left action is the same as the right action. And then we have another map, zeta, which is defined on the abelian group of partial generalized cross product and goes into the first cohomology group, partial cohomology group with the values in this pic S0. So this pic S0 is indeed a partial module in the above senses. It's a commutative monoid with a unital partial action. And this zeta is defined this way. And we prove that this is a group homomorphism. So we have this sequence of two morphisms from pic, this fixed group to C, and from C to Z1. Now, instead of taking the first cohomology group, we take an image of it, and this one. So this is H1 bar. So it's not going to be cohomology group. It is an image. Is going to be, and it can be shown that this will be an image of first cohomology group. This is the first cocycle. So these are Z1. So these are one cocycles. Okay. I said cohomology, so no, it's only one cocycles. Cohomology we get if we cut it. So this is the group of one cocycles, partial cocycles. So we factor this one partial cocycles by image of this composition here, right? Okay, finally we need another group defined by in the paper I mentioned, Gomez Torres in narcotic. So it is formed, consider the monoid formed by this triple. So P is an R bimodule. S, we have an extension of non-commutative unital rings. P is an R bimodule, S is an S bimodule, and phi is a bilinear, R bilinear map with this additional properties, that these maps are isomorphisms. R linear from the left, S linear from the right, the first one, and other way around the second one. We define the product of such triples, okay, this way, and isomorphisms are defined in a very natural way, and then we take the isomorphist classes, those P, which such that P belongs to the Picard group of R, and X belongs, the class of X belongs to the Picard group of S. So this is the group PSR, and they proved in their article, which I mentioned, also Miyashita proved, but Gomez Torres for a bit more general context of local units, they proved that this is a group. So I will need a subgroup. This is kind of those triples such that P belongs It belongs to peak R by definition, but it should be central over Z. So now we fix a unital partial representation and define this kind of invariant subgroup of this PZ delta over R. So now the extension is delta, the cross product over R, the general partial cross product over R, with these properties, right? And so kind of invariance phi p on the right and phi p on the left, and these are equal. Finally, we have the following exact sequence. So this is our final result. So it involves the first cohomology group with values in the second one, the third one. This image of cohomology group, instead of Picard group or Picard semigroup, this intersection appears. So these are those elements from Picard group RZ, which are invariant under the partial action alpha star, which is partially acting on the Picard semigroup. And this is our version of the Brouwer relative Brouwer. Thank you very much. Slava Ukraini.